second talk is given by Professor Ran Yi from Shanghai Jiao Tong University in China. And Ran Yi is currently an assistant professor with the Department of Computer Science and Engineering, Shanghai Jiao Tong University. She received the BE degree and the PhD degree from Tsinghua University, China in 2016 and 2021. Her research interests include computer vision, computer graphics, and computational geometry. She has published over 30 papers in major international journals and conferences, and her talk is about audience-driven talking face video generation. Okay, I will stop my screen share and let Yiran to start her talk.
Okay, thank you, Professor Chen. And I will share my screen. So can you see my screen?
Yes.
Okay, thank you. So hello everyone, I'm Ran Yi from Shanghai Jiao Tong University. In this talk, I will present some works around audio-driven talking face video generation. And so audio-driven talking face generation is one research direction in the cross-modality learning of visual and auditory. And this task aims at transferring a speech signal into the visual information of a target person. So this task involves predicting lip movements, facial expression from speech, and also the head movements. It has many applications in digital human animation, virtual newsreader, and game generation, etc. And in this talk, I will present two works around this task. The first one is audio-driven realistic talking face generation. In this work, we focus on predicting personalized head movements from speech. And this video shows our results.
I needed a job. I wanted a job. I just had my second baby. My second son had just been born like 2 weeks before that.
And the second work is around audio-driven artistic talking face generation. And this paper aims at generating an artistic style talking face video, like of cartoon or line drawing or watercolor or painting. And the right side shows our results.
I needed a job. I wanted a job.
We have the word ache, containing CH, very common combination, and the sound is a hard K, so that the H is actually silent. For example.
And next, I will first introduce the first work. So the title is Predicting Personalized Head Movements from a Short Video and Speech Signal. So natural head movements actually play a very important role in high quality communication. But most existing audio-driven talking face generation works, they use fixed head pose or head pose copied from another video. Some recent works predict head motion from audio, but they fail to address the one-to-many problem for the speech-to-head pose mapping. Actually, we noticed that the mapping from speech to head pose is a one-to-many mapping because there is some correlation between speech and head motion, but the coupling varies from utterance to utterance. This table shows a comparison with methods that predict head poses, but most of them don't consider the one-to-many mapping. Next, I will first briefly introduce some related works in this research direction. In talking face video generation, there is a branch that's the talking face video is driven by some source video. Like in this figure shows, there is a source person that is moving, is making some expressions, and the method aims at transfer the facial expressions in the source person or source video to a target person. And so video-driven methods can be categorized into two subclasses. One is based on traditional optimization, and the other is learning-based. And our task is audio-driven talking-based video generation. And the difference is that the facial expression is driven by a speech signal rather than a source video. And it is rather challenging because it involves two modalities. Audio-driven methods, they can be categorized based on the time span of the input visual information. Some methods use a single face photo to provide the visual information, and some use a short video, less than 15 seconds. Like our method use the second, it can be categorized into second category. And some use 2 to 3 minutes video, and some use very long video, like over 10 hours video to provide visual information. And also some method doesn't constrain the time span of the visual information. In our method, we also use the 3D face reconstruction as a model, as a submodule, because if we want to generate head movement, large head movements, we need to first use 3D face reconstruction to extract the head movements from some videos as the training data. And 3D, we use this 3D face reconstruction method based on 3D And 3D face reconstruction methods also can be categorized into two subclasses. One is traditional method and one is learning-based. We use the second subclass. Next, I'll introduce our method. So the target is to predict head movements from speech. We actually did some investigation in the correlation between speech and head motion, and we found some related works. So from the first related work, one of its conclusion is that there is a weak correlation between speech and head movement. And the second related work, it has a conclusion that the coupling manner between speech and head motion changes from utterance to utterance. So the speech to head motion mapping is a one-to-many mapping. And from the second related work, we assume that a basic utterance unit only corresponds to one head movement pattern, and we assume a basic utterance unit ranges from a few seconds to a dozen seconds. That is often corresponds to a short video of 10 to 15 seconds. From these observations, we define the motion behavior pattern. We characterize the head motion in each short video, that is of 10 to 15 seconds, by a motion behavior pattern. And we think that different people will have different motion behavior patterns. And for one person, there are different motion behavior patterns in the different short videos of that person. And these two videos shows an example. These two videos are of the same identity, but they have different head motion patterns. Yeah.
Hello, I'm Emma from English. In this video, we're going to talk about 4 things that you can do every day to improve your English.
So the first short video of this person only have some slides, head motion.
You want to sound more natural, more casual, more like a native English speaker, right? Some of you also like my not so Australian accent, and you want to practice speaking like me.
And the second short video of this person has a much larger head movement. So we think that even if for one person, he or she can have multiple head motion behavior patterns in multiple short videos. And we think that a short video of 10 to 15 seconds only corresponds to one motion behavior pattern. And in this way, so we can define a motion behavior pattern for each short video. And then if we have the motion behavior pattern, we can predict the head motion from speech signal conditioned on this behavior pattern. And next, I'll introduce how we extract the motion behavior pattern and how we conduct the mapping.
Hello, I'm Emma.
And we represent the motion behavior pattern as a vector in a feature space. And we extract the motion behavior pattern from a short video by 2 steps. The first step is to get the head pose sequence from a short video. And to get the head pose sequence, we use some 3D face reconstruction method. And the second step is to map the head pose sequence into a vector in the feature space. And we use an LSTM-based network to conduct the mapping. And to train the mapping, we conduct a data set containing different styles of head motions. And after we have extracted the head motion behavior pattern, we model the speech to head motion mapping as a one-to-many mapping as this function FAX. Here, A is the auditory feature extracted from a speech signal, and the X is a motion behavior pattern extracted before. And we map the A and X to a predicted pose sequence Y. And since we have this one-to-many mapping, given a fixed speech signal, we actually can change the motion behavior pattern X, so that using this function F, we can get different predicted head motion sequences, so that one speech signal can actually correspond to different head motions using this mapping. Now that we have 2 mappings, one is to extract the head motion behavior pattern, and the other is to predict the head motion. We design 2 networks for these 2 mapping. We design a head motion encoder, EM, for the first mapping, and design a head motion decoder, DM, for the second mapping. And here are the training losses we used to train these 2 networks. So after we proposed this head motion encoder and head motion decoder for the head motion prediction, we then proposed a talking face video generation system based on the head motion prediction model. Our talking face video generation systems can be summarized into 2 stages. The first stage is the stage 1, actually maps from audiovisual information to 3D facial animation. And the second is stage 2. It maps from 3D facial animation to realistic talking face video generation. I will introduce each stage in detail. So stage 1 actually consists of 3 models. The first one is 3D face reconstruction based on 3D MM, and the other is and the second is audio to expression mapping, and third is from the audio and head pose sequence to predicted head motion. So the first one, for the 3D face reconstruction, we use an off-the-shelf 3D face reconstruction network, which reconstructs 5 components from a face photo. The components can be categorized into shape, texture, lighting, expression, and pose. And the second model for the stage 1 is the audio to expression mapping network, and its input is some audio features, and its output is facial expression coefficients. We design an LSTM network to establish mapping. And the third model in the stage 1 is we previously introduced the multimodal input to head pose mapping. We actually just use the head motion encoder and head motion decoder to conduct a 2-step mapping. And the second stage is from 3D facial animation to realistic talking face video generation. It also consists of 3 models. The first one is a rendering model, and the second one is the background matching, and the third one is a GAN model to refine the rendered frames. So in the first model, the rendering model, we actually combine the expression and head pose predicted before with the 3D reconstructed identity, texture, and lighting, and combine these 3D MM coefficients and render them into a video sequence. And second model is a background matching, because the rendered frame does not have any background. So we use the background in the input short video to match the background with the rendered image. We first match for the keyframes which have the most critical head movements, and then we interpolate for the frames in between to neighboring keyframes. And after that, we use a GAN to refine the rendered frames. We use a generator based on attention mechanism and use a discriminator to discriminate the result is good or bad. So for the generator, we use an attention mechanism that aside from output the color mask, it also outputs an attention mask, and the attention mask attends to regions that need to be changed. And the color mask learns the realistic textures. And the discriminator, we adopt a very classical patch GAN network. And here we show some results. We first compare our method with state-of-art audio-driven talking face generation methods. The left shows some qualitative comparison, and we also have a demo video comparison.
I want people to know that you do not have to accept the box that society puts you in. Reinvent yourself the way that you want to. I want people to know that you do not have to accept the box.
So in
this
result, we actually use a
reinvent yourself
audio,
the way that you want
the comparison method.
Let's get started with 2 example words. The first example word that I have for you is ban.
So the comparison methods all copy the head motion from another video. So the head motion does not correspond that well to the input audio. So when the input audio is very slow, the head motion is still very quick, so that it's not very good. But we predict the head motion from speech and the head motion behavior patterns, so we can better generate the head motion. And here are some quantitative comparison. We use several metrics and user study to validate our results. And here is a video showing the pose variety.
Clip, I'm going to tell you the
I want
story.
2 different audios.
You do not have to accept
It all started with a
the
panic attack
box
on national television. clip, I'm going to tell you the weird
I
and winding
want
story
people
of how
to
I went
know
from ardent
that
skeptic to daily
you do
and then
not
public
have
meditator.
to
It all
accept
started with a
the
panic attack on
box.
national television. Clip, I'm going to tell you the weird
I
and winding
want
story of
people
how I
to
went
know
from ardent
that
skeptic to daily
you do
and then
not
public meditator.
have to accept
It all started with a
the
panic attack
box.
on national television.
Since the comparison methods all copy the head motion from another video, so given two different audios, they have the same they have the same head motion, but we predict the head motion. So for different input audios, we can generate different head motions. And here is another video comparison with the ground truth.
I needed a job. I wanted a job. I just had my second baby. My second son had just been born like 2 weeks before that.
I think that there are a couple of things. One, there is actually a hunger for different ideas. The monolithic nature of the.
I want people to know that you do not have to accept the box that society puts you in.
And this shows that given the same speech signal, that we condition on different head motion behavior pattern, we can generate different head motions. And next is an ablation study to show the effectiveness of each model. And here is another ablation study result.
2 miles northeast, then 5 miles southwest, that sort of thing.
This verifies our head motion estimation. And here is a brief conclusion. So in this work, we propose a two-step mapping based on head motion behavior to predict personalized head pose from multimodal input. And based on this mapping, we propose the talking face video generation, which generates high quality talking head videos. And next, I will present the second work that is animating portrait line drawings from a single face photo and speech signal. Different from the previous work, this work concentrates on artistic style talking face video generation. And this work is published on SIGGRAPH 2022 conference track. And so different from the realistic talking face video generation, artistic style, it can invoke different human experiences and leading to stronger visual effects. And it can enable new interaction and entertainment applications. And this figure shows our inputs and output. We actually have tried several artistic styles. Here shows a line drawing and cartoon. We also have tried watercolor and painting styles. And so for this task, there are not very much work in this specific research task. Some methods can conduct the photo to artistic portrait drawing style transfer, but they only deal with a static line drawing generation of static cartoon, and there are some video style transfer, but they require the input is also video, but they cannot generate artistic video from a single face photo and speech signal. And for the audio-driven talking face generation, the main methods they focus on realistic generation, like the previous work. And here shows a realistic generation. SIGGRAPH
is one of the most highly respected venues for the presentation of new computer graphics technology and research.
But these works did not consider the artistic style talking face video generation. So our task is different from the previous works. So the task, the inputs is a single face photo and speech signal, and outputs is an artistic talking portrait drawing video like this.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
And this task, it requires two subtasks. One is the facial changes according to the speech, and the other is style transfer. There are no previous works to address this task, and we actually can combine some existing works to as a simple baseline. The first combination is that we concatenate realistic talking face generation methods and then conduct video style transfer on that. But that causes interference discontinuity problems like this.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
The other way is to combine some static stylization method and then warp the stylized output to generate an animation, but that will cause unnatural and fake when under large head movements like this video shows.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
So these combinations, they both cannot generate very good results.
For example,
so to solve this problem, we propose a new feature warping framework to generate artistic and expressive talking, audio-driven talking face video. And we conduct both geometry change and artistic style transfer using a single GAN model, learning from static portrait drawing data, and ensure temporally coherent animation via two new coherent source terms. And we also propose a scheme to separate the processing of foreground and background to avoid inappropriate background warping. Our framework can be categorized into two stages. The first stage is to predict facial landmark from the speech. So in this framework, we use the facial landmarks as an intermediate representation. We first translate the speech to the facial landmark movements, and then to generate a new artistic video based on the predicted landmark sequence. And for the audio to landmark translation, we actually use a Make It Talk. We use the audio translation model from Make It Talk, and this network contains two branches: one speaker agnostic branch and one speaker related branch. We mainly focus on the second stage, which is the talking portrait drawing generation from the landmarks and the face photo. In this stage, we have to solve two challenges. The first challenge is to simultaneous style transfer and facial geometry change. And the second challenge is how to ensure temporal coherence from unpaired static data. To solve this first challenge, we propose a new generator based on feature level warping. We conduct warping on in the feature space to align the face image features to the target geometry. We warp the image feature according to some predicted flow map, and then apply the feature warping on multiple scales. So this feature level warping helps us to align the source geometry to the target geometry. And to cope with the generator, we also designed two discriminators. The first is a drawing discriminator, which discriminates whether the generated result is a good artistic style drawing or not. It contains it contains a global discriminator and 3 local discriminators for important facial features. We also designed a temporal coherence discriminator, which discriminates whether 2 joins are temporally coherent or not. And this network is only used for line drawing style, where we use a color portrait film and extract the lines as and approximate data for the line drawing. And for the other styles like cartoon or watercolor, since we don't have the real examples, we don't use this network. And for the loss functions, we designed 6 loss terms. The first 4 loss terms are used to solve the first challenge, that is to simultaneous conduct style transfer and facial geometry changes. It consists of an adversarial loss for GAN and warping-based content loss, and also a geometry loss based on landmark detector and an identity preservation loss. The last 2 losses are designed for to ensure temporal coherence. The first temporal coherence loss is based on interframe warping. We generate 2 drawings conditioned on 2 target landmarks, which have slight changes. And we warp the first generated drawing to the second target landmarks. And we constrain that the warped results should be similar to the second generated drawing. So this warping-based interframe loss can help ensure the temporal coherence, since adjacent frames often have very small changes in the facial expressions. And the second temporal coherence loss is based on the coherence discriminator, and this is only used for line drawing style. And for the discriminator, it needs real samples and fake samples, since we only have unpaired static data. So we generate some approximate data as the real samples. We use a color portrait film and extract the lines of it. And we take the extracted lines of adjacent frames as the approximate real samples, and the extracted lines of non-adjacent frames as the fixed examples. And also the generated drawings conditioned on 2 slightly changed target landmarks are also considered as fixed samples. And apart from the architecture and loss terms, we also design a foreground-background separation strategy. This is used to avoid undesirable background warping effects. We can show in this demo video.
And I don't know when your moment was.
Here is a teacher in front of a blackboard, and there are some text on the blackboard. That's when she speaks, the blackboard should not move, and also the text on the blackboard should not move. But if we do not use the foreground-background separation, the background will warp with the foreground.
But I bet you there was one.
This example shows.
But I bet you there was one.
So we separate the foreground and background processing to avoid this background warping effects. So we first conduct foreground extraction, and we generate foreground drawing using our proposed generator. And then for the background drawing, we use some static generation methods to make the background does not move. And then we blend the foreground and background results together. Next, we show some experiment results. First, this page shows some training data. So for line drawings, we mostly use the artistic portrait line drawings we collected from some websites. And these are only contain static drawings and unpaired data. And to train the temporal coherence discriminator, we extract some line drawings from a color portrait film and get these results. It can be seen that the extracted line drawings are very different in style from the data we collected from websites. So it is only an approximated data, but not very exact. And for the cartoon style, we only use the static data and does not use any video data. Here shows some comparison with baselines. For baselines, we actually combine several methods together, like here ATVG and SDA are some realistic talking face video generation methods, and UPD is a line drawing stylization method. So we compare our methods with these combinations.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent. For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
And we also compare with other baselines.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
And I don't know when your moment was, but I bet you there was one.
For example.
And I don't know when your moment was, but I bet you there was one. And I don't know when your moment was, but I bet you there was one.
And here are some quantitative comparisons. We conduct a use study and also use 3 metrics to compare with the baseline methods. And here shows results on other styles containing cartoon, painting, and watercolor.
And I don't know when your moment was, but I bet you there was one. And I don't know when your moment was, but I bet you there was one. And I don't know when your moment was, but I bet you there was one.
And so a brief summary, in the second work, we proposed a novel feature working framework to generate an expressive artistic talking face video from a single face photo and a speech signal. And we firstly proposed the method for line drawing style, but then we extend the method to other styles, including cartoon, watercolor, and painting, and generate high quality results. And we also make the code open source. You can visit this GitHub page to try the code. And that's all for the talk. Thank you.
Thank you very much, Yiren. Very nice work. And I'm not sure. Any questions from the audience? Well, I want to ask you a question about your first work. And I see that you generate the face part according to the 3D model to synthesize the animation of the face region. But how about the hair regions? It seems that, I mean, you have a mask for the hair area, but how it is related to the pose?
Okay, I will show the screen again. So actually, in our framework, we consider the hair as a part of the background. So actually, when we match we conduct background matching, we will match the rendered face with the background that has the most similar head poses. So when we do the background matching, we will find a background with the most similar head pose with this rendering, so that the hair will will cope with the face.
Consistent
better.
with the 3D face pose, right?
Yeah, right.
Okay, good. Have you ever applied your second work to the 3D animation?
We haven't applied that because in the first one we used 3D face, but the second we didn't use 3D. So in the second
The second one, yeah, the second one doesn't have the 3D pose.
Yeah, but I think it can also use 3D in this in this framework. We can change the audio translation model and maybe change the condition to a 3D face components.
Yeah. Another question about your first work, and it's in order to represent the motion behavior, it seems that you say map the motion behavior into a vector, just a vector, right? Is it related to the length of the video, or you use fixed length of the video to map several frames into a fixed dimensional vector?
Yeah, actually, we think each short video corresponds to one motion behavior pattern, and we actually constrain the short video to 10 to 15 seconds.
Okay,
Yes.
so you use fixed length. You just segment a long video sequence into several segments, pieces, right?
Yeah, right.
Thank you.
Thank you.